Okay, so hopefully by now you guys have gone ahead and uh, worked through number two. So basically for number two, it says, what is the relationship between the base of AB of the trapezoid, trapezoid ABCD, and the graph of the function? So you just want to say something along the lines that side AB, that's like the lower limit, that's the x equals 1, the vertical line that's creating the lower limit of the function. And then the same thing with base DC. It's the upper limit of the function of the integral. We find the area of the trapezoid, and the area should be 35. I think is what I got. So it should be 12. Yeah, I think 35 sounds about right. It definitely should be an overestimate. I don't have my calculator with me today, so I was not able to run the actual integral through the calculator at the beginning. Was somebody able to do the integral at the very beginning and get their area of the function at the very beginning of the problem? Somebody have that written down. And that's kind of what problem 2 is going to look like. Now, for problem 3, we find a better approximation by breaking this into 5 evenly spaced trapezoids. And we should be able to answer all of these questions. The height of each of these trapezoids, or the width of the strips of each of the unit, is 1. Okay, how is it found? It's found because we say the integral goes from 1 to 6. X equals 1 to x equals 6. And we divide that distance by the number of trapezoids. So maybe putting that into words might be a little tricky for you, but hopefully you're seeing what you're supposed to do. All right, that you're like to find the width of each individual trapezoid. Maybe you could see, hey, each one of those is going to be 1. All right, but the bigger question is, why is it 1? How do we find that? That's really what this investigation from your textbook is trying to get out of you. Okay. Then for the second part, let the parallel sides of the trapezoids is the length of AB, and y5 is the length of DC. How can you calculate the length of y1, 2, 3, 4, and 5? So how do we calculate the lengths of everything in between? Okay, what do we think we gotta do to calculate lengths? That's the trick for each of those. Anybody have any ideas to calculate the lengths of this line here? That would be y1, y2, y3, y4. Anyone have any ideas? I don't need to calculate y5 actually. I just need to calculate 1, 2, 3, and 4. But how would we calculate those lengths? Yes, plug it back into the original function. Exactly. Take the original function and you just say, let's plug in 2, since I know that's where this is right here. All right, so 2's the y value, and I do get a 6 for the, or 2's the x value, I do get a 6 for the y value, which is good, that checks out. And then I can plug in 3, and I'm going to get 4 for the y value. I can plug in 4, and I'm going to get 3 for the y value. And when I plug in 5, the last one, this is the only one that's going to be a weird decimal. It's going to be 12/5, which is like 2.4. So that's the only one where you really have to kind of think about what's the height of that going to be. All right, but now we found all of the bases. So y1 is 6, y2 is 4, y3 is 3, y4 is 2.4, and y5 is 2. We know the height is 1 of each one, and then we're just finding the individual areas. Okay, the bases added together, 18, divided by 2 is 9 times 1. So this one's 9. The second one, 10 divided by 2 is 5 times 1 is 5. Third one, 6. Right? No, hold on. That shouldn't be right. 10. The third one's 12 divided by 2 is. Oh, third one's 7. Sorry. Divided by 2 is 3.5. That makes more sense. The next one's going to be 5.4 divided by 2. That's 2.7. The last one's 4.4 divided by 2 is 2.2. And then we can add all of our areas together and hopefully get a more accurate area than what we had before. Plus 4. So I think I ended up at 22.4 is my sum. I just did that in my head, so let's make sure that's right. 14, 17.5 plus. Yeah. So yeah, I think it's 22.4 is what I'm coming up with. And then, is this estimate better than the estimate for S found in 1? The answer is absolutely yes, way better. All right. Because the estimate before was 35, and now we're at 22.4. And then why is it better? I'd say it's better because each trapezoid was closer to the actual curve. All right, so that's what's going on there. And then how can we improve this value? What's an easy way to improve the value if we want to say we want a little bit more accurate of an estimate using trapezoidal area? We could, add more trapezoids, exactly. And your textbook does go on and ask you to find more trapezoids, but I feel like at this point, we've kind of got the idea. We already did it with the rectangles, all right. So I didn't see the worth in having us do it one more time. With your textbook asks you to do it with 8 trapezoids and then work through this whole problem again. But I do think it's important to see just here with the 5 trapezoids. Does this make sense? So like if there's a question like this on your test and I'm asking you to use either a rectangle rule or trapezoid rule to do this, do you know how to find the width or the height of each one? And then do you know how to find the width of each one? All right, so by plugging in the values and showing all of your work to do that. All right. So the trapezoid rule, this is the rule from your book, is this integral from lower limit a to upper limit b of f of x dx. And then it says it's approximately 1/2 times the upper limit minus the lower limit divided by n times all that. So basically what it's saying is you can plug in the upper limit and the lower limit for these values. All right, and you can do 1/2 times that number, and then you can multiply all of your y value or add all of your y values together, and you can kind of do it at once instead of doing each individual trapezoid. That's the idea with the trapezoid rule. So it's just meant to save you some time if you're calculating with the trapezoid method. Okay, and I think we can do one example where we try it out. Okay, that's the goal for today. All right, so now, so it says where the interval a is less than or equal to x is less than or equal to b is divided into n intervals of equal width. Okay. All right. So now, to look at this part, it says what is the value of x sub I when I equals 0? Okay, so when I equals 0, I'm trying to see where is I in this rule anyway. I don't even see an I in this rule. Anyway, this is saying when there are no trapezoids. Okay, so all right, so there are no trapezoids. That's what I equals 0 means. Okay, and then let's see. I assume that xi must be the value of b minus a over n. Your book doesn't really specify it. Let's see here. Yeah, that's kind of weird. What your book's trying to get at from this. So then what's the value of xi when I equals n? Let's see. Yeah, again, I don't know. I put this down here, but I'm not sure what your book is asking, honestly, with these two questions. I was just in type it up mode. The last part, though, b minus a over n in this formula, I could explain what that means. I know what your book's trying to get at from this. That's where we're doing the upper limit is b minus the lower limit of your integral, that's a, divided by the number of trapezoids. That's n. That's what this last part's asking us right here. So b, a, n. Okay, so that's what the last part's talking about there with the meaning of b minus a over n in the formula. All right, so example 8 asks us to estimate the area under a curve over the interval 4 is less than or equal to x is less than or equal to 12 with x and y values given in the following table. Okay,
Can you scroll up a little bit?
I'm sorry?
Can you scroll up a little bit? Sorry.
There we go. There we go. Yeah, so for this one, when you're given these values, it's telling you, hey, the x value at 4, the y value is 5, and then when x equals 6, the y value is 13. So basically what we're seeing here is we're seeing, if we were to graph it, you can see that there's a height of 2 basically. So let me sketch a quick graph of this function just to give you an idea of what the visual looks like for it. So when x equals 4, we're going to have a y equals 6. We'll say something like that. And that means you could draw a trapezoid from there, and then you go to 6 and 13. 5, 6, all the way up to 13. And just saying you can draw a trapezoid for that stretch. Basically, this is what this means. And then when we go to x equals 8, whoops, I need to let somebody back in. And when x equals 8, we can draw a point at 10, and now we can draw another trapezoid. And we can do this for all of these values, basically. That's what this problem's telling us when it's saying estimate the area under a curve. When it doesn't give you the equation, but it gives you the table. And we know the width of each of these trapezoids, or the height of each of these trapezoids, is going to be 2. They're evenly spaced, so our height is 2. So I should be able to make 1, 2, 3, 4 trapezoids here. And that's how I can find the area under this specific interval. So the first trapezoid, 1/2, my bases are 5 and 13, and my width is 2. So trapezoid 1, base is 5. I've got a base of 13, height of 2. That's where those numbers are coming from to set up my first trapezoid. If I have a problem visualizing it, then that's what the picture is here for. This is my height of 2. Here's my base of, oops, I said 6, but it's actually 5. So, and then height of, so this should be a 5, not a 6. Oops. There we go, 5, not 6. And then the second height was 13. And that's the idea here. We're just creating the first trapezoid, and we're finding the area of that particular trapezoid. So what I want you guys to do is take a minute and go ahead and calculate all 4 trapezoids, and then add them all together, and you're going to find the total estimated area of this particular curve. That's the idea for this problem. So give that a try, and I'll write it down while you're working on it too. All right. For example 9, this one's another one where it says estimate the area under the curve of the graph f of x equals e to the x. So now we're looking at exponential functions and logarithmic functions. And again, it just says using 5 trapezoids. So that's kind of the key here, and it's the interval from 0 to 1. So we have to do kind of our knowledge from the investigation here. I need to, oh boy, got an excited dog downstairs. So what I need to do here is come up with 5 different values. So I'll start with 0, and I'm going to go all the way to, oops, I need to do a 6th value, sorry. All the way to 1 for my x values. And then I'm going to break it down into intervals of fifths, right? So 1 divided by 5, because that's the interval, it's 1 minus 0 divided by 5. The upper bound minus the lower bound divided by the number of trapezoids, and I get 1/5 or 0.2. So that's what I want to break all of my trapezoids down to: 0.2, 0.4, 0.6, 0.8, and 1. And now you can plug in that value for x and find all of your corresponding y values, and then you're going to use that trapezoid formula again. I'm going to ask you guys to go ahead and get started on that. I'm going to go check on my dog. We're all on the front lawn. It was very exciting. You know how it goes. Anyway, for problem number 9, this is actually a good one to use the trapezoid formula on, just because we're dealing with this e. I don't have a calculator on me, but I do know that e to the 0 power is just going to be 1. And then I can do e to the 0.2, e to the 0.4, e to the 0.6, e to the 0.8, and then just e to the first power would be the last number. And if I'm using the trapezoid formula from up here, where it says the trapezoid rule, I can go ahead and write the integral from 0 to 1 of e to the x dx. And I can say that's 1/2 times my upper boundary minus my lower boundary over 5. Okay, so that's the 0.2 times, and now I can just add all of these things together. It's going to be the first term plus the last term. What's the last term here? The last term was... oh, the last term, the first term was 0, sorry. 0 plus 1, plus, and then it calls for a 2 times, and then all of the other y values. It's going to be e to the 0.2, e to the 0.4, plus e to the 0.6, plus e to the 0.8. So I did have it right, it was 1. Sorry, it's the first term and the last term, the first y value and the last y value, so it should be 1 plus e plus all of these terms times 2. Okay, and then we can go ahead and plug that into our calculator, and that'll save time for us trying to calculate this trapezoid rule. That's the purpose of this rule, and that's how we would use it, is we plug in the first term, which was the 1. That's what the y1 was. So let me just highlight some stuff for you here. The first term was the 1. The last term was the e. And then we do 2 times every other term, because if you think about when we're doing trapezoids, we're going to add each of these terms twice, technically. And that's why it's 2 times each of them, because you're doing it on the right side for one trapezoid and the left side for the other trapezoid. So like when we're doing trapezoids, we're doing the first term once, and then this term to make that first trapezoid, and then the second trapezoid, we're doing this one and this one, so this value is being used twice. That's exactly what I mean by using the term twice. That's why it's at times 2 there. Alright, to help try and make sense of this trapezoid rule. And we plug that into our calculator, and we should end up getting 1.724 other stuff, and we can just round it off to 1.72. 3 significant figures should be good. And that's what the trapezoid rule looks like for problem 9 there. Okay. The last problem here, example 10, the cross-section of a river is shown here. If the water is flowing at 0.8 meters per second, use the trapezoidal rule with 7 trapezoids to find an approximation for the volume of water passing through, passing this point in 1 minute. All right. So the nice thing is that we're going at least to 7 points. That's nice. So each one will be 1 trapezoid. So like our first trapezoid right there, second trapezoid right there, third trapezoid to point D, there we go. So there's all of our trapezoids right there. Alright, so we want to go ahead and use the trapezoid rule to figure it out. Okay, so it says it's flowing at, let's see. Let me help you out to get started. So what we can do with this one is we can actually set up a table to represent our x and y values first. Just look at where your points are on the graph. So point A, for example, is at 0, 4, and point B is at 1, 3, and point C is at 2, 1. And what you can do with each of these values is you can use the y values for the trapezoid rule. So these are the y values you're going to want to use. So that's why I'm trying to point that out for you here, because it's kind of a weird looking graph. It might be a little bit confusing for you, trying to make sense of what it's saying here. Alright, so setting this problem up, I started it and I said we're doing the 1/2 because that's the part of the trapezoid rule, and then we're doing the height of each trapezoid. So in this case, the height of each one is 1. We can see that up here. They're just a distance of 1 apart. And then we start using the y values from here. So I used the first 4 I highlighted in red, and then the last 4 I highlighted in green there. And I did +2 times, and I'm going to do all the other heights added together. 3 plus 1 plus, I guessed at 0.04, plus 1 plus 2 plus 3.4. And I made up the 0.4 and the 3.4. You guys can make that up too. I mean, so you could have said 0.5 and 3.5. That's perfectly fine. Your answer might be a little bit different. but that's the idea here. Okay. And then we go ahead and plug this into our calculator and we should get our answer. And what do we get? Like 14. 14.8. That's if I'm using the 0.4 and the 3.4, I think. So I'm getting 14.8, and because it was in meters, they told us it was meters. I'm going to say 14.8 meters squared. Okay. All right. All right. So any questions on this problem here? Okay, good. So then your assignment over the weekend then, I'm just going to ask you to practice with the trapezoid rule. So problems 1, 2, and 3, I'm only asking you to do the odd problems. So problems 1 and 3 are asking you to estimate the area under the curve. So that's going to be like an example 8 type situation. And then after that, when we get to problem 5, you can estimate using the data points, using the trapezoid rule. Problem 7, sketch the curve and shade the region. And then you're going to write down a definite integral and find the area. So this is going to be like a previous assignment type problem. Okay, so that might take you back to earlier in the unit. And then problem 8, consider the region enclosed by the graph. And then sketch the function, write down the integral. So it's just practice using these trapezoids. And it's kind of trying to put everything we've learned together so far. That's the idea with the assignment tonight. So odd problems 1 through 7, and then problem 8, 5 problems total. All right. Anyway.